Here is classwork problem 1. We are taking the region bounded by the x-axis and this curve. So let's just sketch that. I know this is a parabola whose x-intercepts are 2 and 6. So this region right here is the region that I'm rotating. For part A, I'm going to rotate it about the x-axis. So I'm going to sketch the reflection of what it looks like around the x-axis. And then I imagine each of these bars rotates out of the page to form a disk, like this. So the question that you want to ask yourself, it would be easy to find the volume just by integrating the area of all of these disks. Is it easy to find this radius? The answer is yes. The radius is just the height of that curve. So there's no reason not to use the integral involving the disks. So I can integrate from 2 to 6 for the area of each disk, which is the same thing as the integral from 2 to 6 of pi times the radius squared. And here the radius is x minus 6 times 2 minus x, all of that squared. You should finish by evaluating this integral, but I am not. I'm just going to take you as far as the integrals. Alright, so that's part A. Part B. Let's start with the same setup. So we've got the parabola that goes from 2 to 6. Only now we're going to find the volume of the solid when we rotate it around the line x equals 4. So here's the line x equals 4. So in this case, we're rotating it kind of out of the page around this way. So each of these is going to form a little disk. Okay, we could do the same thing. We could integrate across all of the disks in this direction. Only the equation that we have doesn't tell us what this radius measure is directly. We could try and change the equation to tell us what this radius was and then integrate from y equals 0 to y equals 4. But instead of doing that, I'm actually going to use shells. So if we imagine here's a shell and there's a smaller shell, sorry. So in this case, we're going to start integrating from 4 to 6 because we're starting with a shell that's just a really small shell that's right around the axis of rotation here and going out. So if we're integrating by shells, that's going to be an integral from 4 to 6. And the equation for the volume of this shell is going to be the circumference times the height times the thickness. So the circumference is 2 pi times the radius. In this case, the radius isn't just x. The radius is the distance from the axis of rotation here. So the distance is going to be x minus 4. So for example, when I'm considering the shell at an x-coordinate of 5, the radius is actually 1 because it's 5 minus 4. Gives me the distance from the axis of rotation. So that's the radius. The height is the same thing that it was before. It's x minus 6 times 2 minus x. And then the thickness is dx. Let's do problem 9. In problem 9, we are looking at the area of the region bounded by all of these curves. So let's sketch them. I've got x equals 2. Well, let's start with the 4 over x. So this is the same thing as 4 times 1 over x, and I know 1 over x has this general kind of shape. And I've also got a piece down here. I guess I'll draw it. And now we're looking at x equals 2 and x equals 4, so that's here and here, approximately. So, and y equals 0, which is the x-axis. So this is the region that we're considering. And they're telling us to revolve it around the line y equals -1. So here's y equals -1. So if I'm going to revolve this around -1, I'm going to get this same shape reflected on the other side. doing my best to sketch the reflection. Right, so this has been revolved that way. So it's going to be this kind of solid shape with this hole running through the middle here. And the hole running through the middle is always the same diameter. And then we've got these outside parts. Okay, is there any reason not to integrate all of the washers? Let's think about the two radii. This inside radius is always 1. That's easy. The outside radius is going to be 1 plus the height of the curve, so that's also easy. So we'll do the integral from 2 to 4 of pi times the large radius, which is 1 plus 4 over x squared, because it's the large radius squared, minus the small radius squared. The small radius is 1, so that's 1 squared, which is 1, dx. Okay, and then you could evaluate this. This is problem 10. In problem 10, you have this equation, which might freak you out because it's the reverse of what you're normally expecting. So this is a case where I think it would be fine to consider the region that's the reflection across the line y equals x. So in other words, we can find the inverse functions here. So we'll swap x and y. And the volume of the shape is going to have the same volume because we've just done a reflection, which doesn't actually change the shapes or distances involved. It's a rigid transformation. So I've swapped all the x's and y's. Let's kind of sketch this thing to see what it looks like. Well, this one's easy enough. This is what we're revolving around. Let's factor this to figure out what it looks like. So I'll have a negative sign out in front, and I'll have x squared plus 6x minus 8. Which is going to be minus 4 minus 2. That makes sense. So if I sketch this now, I've got a curve with intercepts at 4 and 2. And I know it's an upside down parabola because of the negative coefficient out here. And it's being bounded by y equals 0, so that's this line, so it's this area. But now we're revolving around x equals 1, which is this line right here. So let's see. So this is a distance of 2, so if I have a parabola on the other side, it's going to look like this. And it's going to go, so this was x equals 1. This is the x-axis here. So it goes from 0 to negative 2. Alright, so let's imagine the rotations here. So we've got these as kind of the hole in the middle. And then this is all part of the area here. So this is all kind of part of the area. Okay, so could we use washers here? Well, we could use washers, except we don't really, this form of the equation doesn't really tell us what these x distances are. So instead, I'm going to use shells. So let's imagine a shell here. So if this is my shells, I'm going to integrate starting at 2 and going out to 4. Because 2 is the closest in to the axis of rotation that my shells start. Actually, yeah, let's do that, from 2 to 4. So, let's see, the equation for the volume of my shell is going to be 2 pi r times the height times the thickness, which is dx. So we have to think, what is the radius and what is the height? So if I'm starting to integrate here at 2, the radius of my shell is going to just be x. Because even when I start at 2, the radius of this shell right at 2 is still x. And the height is the height of the function here. So that's going to be negative x minus 4 times x minus 2. and the thickness is dx. So here, let's move the negative sign outside the integral. There we go. So that would be the integral that you could then evaluate, which is what you should do. Okay, let's do problem 4. This is a good one. So they're saying consider a solid that has its base, that has as its base the region in the xy plane. So let's draw the xy plane, determined by the graph of the equation x squared plus y squared equals 25. As you know, this is a circle with radius 5. So I'm drawing the circle here. And it's saying it has a bunch of cross sections in a plane perpendicular to the x-axis. So here's the x-axis. So a plane perpendicular to the x-axis would be this way. And it says all the cross sections are isosceles triangles with a height of 4 inches. So that means I've got a bunch of isosceles triangles with the exact same height and different bases, all kind of coming up out of the page like this. When you're doing a problem like this on the AP test, you want to check to make sure that the shape you're drawing is correct, and you also want to check to make sure that the direction you're drawing it is right. So I'm just double checking. Yep, these are definitely perpendicular to the x-axis. Okay, so if I want to find the volume of this strange shape here, I hope you can kind of imagine this is a shape. I want to integrate from this side to this side, and I want to integrate the area of each of these triangles, because if I add up all the little triangles, all the little slices, that's going to give me the overall volume. So I'm going to do an integral from -5 to +5 of the triangle area. Great idea on the AP test to write intermediate things like this so that you can pick up partial points. So I'll say this is the isosceles triangle area. How do you spell isosceles? Isosceles triangle area. Okay, so what is the isosceles triangle area? Each of the here, I'm going to just sketch one of these triangles. So like let's say it's this one that I'm sketching over here. So I know the height is going to be 4 because they told me. I know this part is going to be the distance from the x-axis to the top of the curve here. So if you wanted to figure that out, we could solve our equation for y, because that's what we're trying to figure out, is the y value here, the height. So if I solve it for y, I've got y squared equals 25 minus x squared, or y equals the square root of 25 minus x squared. So that's what describes this distance from the x-axis to the top of the curve. But the base of the triangle is twice that distance. So that means my area equation is going to be 1/2 the height times the base, which is 2 square root 25 minus x squared. Alright, so this 2 cancels with that 2, so I'm left with 4 root 25 minus x squared. So that's my area. So that means I can rewrite my integral from -5 to 5 of this area equation, which is 4 times the square root of 25 minus x squared dx. And you could then proceed to evaluate that yourself.